Telomeres, the protective caps of repetitive DNA sequences at the ends of chromosomes, play a crucial role in maintaining cellular stability and genomic integrity. Each time a cell divides, telomeres naturally shorten, acting like a molecular clock that limits the number of times a cell can replicate. When telomeres become critically short, cells enter a state of senescence or undergo programmed cell death, effectively halting their function. While this mechanism helps prevent uncontrolled cell division, it also contributes to tissue aging and functional decline. As such, shortened telomeres are not just markers of biological age. They are active participants in the development of several major age-related diseases, including cancer, cardiovascular disease, and immune dysfunction. One of the most direct and dangerous consequences of telomere shortening is genomic instability. When telomeres become too short to protect chromosomes, DNA ends can fuse or break, triggering mutations and chromosomal rearrangements. This sets the stage for cancer, where cells evade normal growth controls and proliferate uncontrollably. Indeed, multiple studies have found that individuals with shorter telomeres have a significantly higher risk of developing various types of cancer, including lung, bladder, gastrointestinal, and breast cancers. While the body tries to suppress tumor formation by pushing critically short telomere cells into senescence, this very process can create an inflammatory microenvironment that paradoxically promotes tumor growth in nearby cells. In the cardiovascular system, telomere attrition is strongly linked to endothelial dysfunction, the breakdown of the inner lining of blood vessels, which contributes to atherosclerosis, high blood pressure, and heart failure. Short telomeres in vascular cells impair their ability to repair damage, leading to plaque formation, arterial stiffness, and an increased likelihood of blood clots. Several large cohort studies have shown that individuals with shorter leukocyte telomeres are more likely to suffer from coronary artery disease, stroke, and heart attack, independent of traditional risk factors like cholesterol levels or smoking. The underlying mechanism appears to involve not just cellular aging, but also chronic inflammation and oxidative stress, both of which shorten telomeres and damage vascular tissues. The immune system is another area where telomere length has profound implications. As we age, our immune cells, particularly T lymphocytes, undergo repeated divisions in response to infection and inflammation. Over time, their telomeres shorten, reducing their ability to replicate and mount effective immune responses. This process, known as immunosenescence, leads to a weaker defense against pathogens, poor vaccine responses, and an increased susceptibility to infections. It also contributes to a rise in autoimmune conditions and chronic inflammation, both of which accelerate aging in a feedback loop. People with shorter telomeres often show a higher burden of inflammatory markers and diminished immune function, a hallmark of frailty and reduced health span in older adults. Adding to this picture is the fact that telomere shortening does not occur in isolation. It is influenced by genetics, but also by environmental and lifestyle factors such as smoking, obesity, lack of exercise, chronic psychological stress, and poor nutrition. These exposures create oxidative stress and inflammatory conditions that accelerate telomere loss. On the flip side, healthy behaviors, including physical activity, a nutrient-dense diet, stress reduction, and adequate sleep, have been associated with longer telomeres or a slower rate of telomere attrition. This suggests that while telomere length is partially inherited, it is also a modifiable marker of aging and disease risk. In summary, the connection between shortened telomeres and age-related diseases is both mechanistic and predictive. Telomere erosion undermines the body's ability to maintain genomic stability, cellular regeneration, immune surveillance, and vascular integrity, paving the way for cancers, cardiovascular events, and immune dysfunction. Monitoring and preserving telomere length is not just an academic interest. It offers real potential as a target for early detection, risk assessment, and prevention strategies aimed at slowing the aging process and extending healthy lifespan.